Alright, time for another DraftPhysics.com video presentation. DebatePhysics.com also, but nobody will debate the essence of the subject. And the subject, primarily right now, has been the kinetic energy theory, the idea that there's two ways of describing motion in the universe, mass and velocity, and that's it, or 1/2 mass and velocity squared. So this idea that there's a velocity squared, or there's a time squared, or that there's something other than squares of stuff rather than non-stuff. But anyway, and there's lots of arguments why they have it wrong. That energy really is only one thing, it's momentum. There isn't any other kind of energy. There's no scalar energy. There's just vectors. Things move in directions and they have a mass and a velocity. And it goes all the way back to gravity and an understanding and how they understand it. And the fact is they cheat the truth. They imply that Newton believed this, or Galileo, or Descartes, or any of the founders of physics and science had anything to do with this belief they have. Okay, so we'll start with what he says, and then I will give you the truth. Okay, what will be found to be the actual function of gravity, the actual mechanism. It's not a magical bent geodesic. It's not some sort of nothing. It's not some pulling force. It's a push universe. Things only move because they're pushed. There isn't any other kind of motion created. And on and on.
What we're really going to talk about in this lesson is the acceleration due to gravity. When we drop things, things fall down, and at a known reproducible rate that is always changing, right? In other words, we drop something, and it speeds up over time, so that's called an acceleration, right? So what we want to do is introduce the gravitational acceleration.
But it's nothing different than just a change in your velocity. The acceleration isn't some special thing. It's just changing your velocity. It's adding to it, subtracting from it. It's just a hunk of it. You have a thing called velocity. I can add to it. I can give you more velocity, or I could subtract from it. I could take away half of it. That's all. It's just a substance, an amount of something, and you just add it. So acceleration isn't some squared thing. It isn't like here's your acceleration, and now we're going to square it. No. Your acceleration is just adding, and all you're really saying with gravity is you're going to add a certain amount per a unit of time. So per second, per 1 second, per each second, you add this much to its velocity. And that's all it is. There's no per second notions. There's no idea that it's a squared function. It's not. That's just wrong.
We'll talk about what it is, what the value of it is, and then we're going to talk about one of the most, I mean it when I say it, one of the most interesting, fundamental, mind-blowing things in all of physics, and that is when you...
So he calls it mind-blowing, but to me, this has never blown my mind. As soon as I was informed that every atom will do exactly what the big thing will do. So you have the Earth going around the sun. I put one atom next to the Earth. It does exactly the same thing. Okay, so it's the real effect is happening to the little tiny bits inside of the big object. It's not the object that's affected by gravity. It's the electrons and protons. They're the universal quantized standard bit. So there's nothing mysterious about me saying, if I have 3 pens and I drop one over here and it drops at a certain speed, and then I have a pen made out of 2 pens, it has 2 molecular bits, it has 2 atomic bits, 2 electrons. Why would I think these, because there's 2 of them, would fall faster? They're not going to fall any faster. They're 1, 1, and 1. Every substance is just made of more of the same things, the same individual units, the electrons and the protons, and they fall at the same rate in gravity because they're affected by the same universe all the time. And so whatever force I apply here, because there's 2 of them, won't mean it can go any faster. Obviously, the one will fall the same rate as this, and this one will fall the same rate as this. There'll be no difference in how they fall, because they're all individual little units. And the little individual units are what are being pushed by gravity. not anything else. The whole mass isn't being pushed. The electrons and protons are the things that do all the moving. Everything that happens in the big universe happens on the small universe first. The electrons and protons have to do it first.
Take two objects and you drop them. Even if the masses are different, they will hit the ground at the same time. I encourage you to try it. Grab a marker, something like this.
So I don't know who these people make these videos for, but I mean, obvious anybody watching a physics video that even has any hint of being about some physics subject probably already knows this.
Grab a paperclip, drop them at the same time from the same height, and they will hit the ground at the same time. The only time in which it doesn't really happen is if I drop the sheet of paper, it's going to flutter to the ground, but that's only because of air resistance. So if you suck all the air out of a...
So this is for like a 10-year-old or an 8-year-old, somebody who hasn't really heard this already? I don't know. I mean, who's the video for?
Container, like in a vacuum chamber, or if you go to the moon, for instance, where there's very little or no oxygen on the moon, no atmosphere, then literally any two objects you drop will hit the ground at the same time. In fact, we did this experiment on the moon where astronauts dropped a feather in one hand and a hammer with the other. In the other hand, there's no air to slow anything down. On Earth, the feather will flutter down, but on the moon, they just both went down toward the ground and hit the surface of the moon at the same time. So we want to talk about that. If you stick...
So again, we want to talk about that, but he's not going to explain that. And he's certainly not going to explain it in what I would call reasonable terms. So I will do that for you. So this is the only place you're going to hear this, okay? Apparently. As far as I know, on the whole surface of the Earth, there's nobody correctly describing how the push force of gravity functions. No one. Not a single person. Except maybe when somebody's talking about mock gravity, when they're explaining the most complex elements of relativity, and they use a gimmick called mock gravity. And it actually is the real gravity, frankly, which is another irony, a funny bit, that they call it the mock part when it's actually the legitimate, closer to the truth than their story. So the point is you have an object, and the object can't be understood as an object. It has to be understood as it's just electrons and protons. So all you're really saying is how many bits does it have when you ask what its mass is. So I could say if something weighed 100 pounds, I could just say, look, it has 100 of these little bits. It's made of 100 bits, okay? And something that's 10 pounds is 10 bits. And the bits are all that are, they're little independent bits, and they're the thing going to be affected by the gravity. And so in the simple argument is that gravity is a force, it's doing the same thing, okay? It's the inverse square law. It's doing the same thing light does. So the further away you are from a light source, the less light hits you. Because what's happening to the little bits of light? Well, the little bits of light leave the sun, for example, and as they get further and further, as you get further and further away, the separation between the bits, that is how far away the bits are from each other, gets further and further, right? This distance gets bigger and bigger. And you have to understand that, that distance is growing in 2 dimensions. So it's getting bigger and bigger in 2 dimensions. That's the square. Okay, the square is created by the fact that the photons are getting separated as they go distance in 2 dimensions. They're separating this way and they're separating this way, and that's the square. So that's why it diminishes twice as fast as you would think it does. It gets 4 times really, because it's in 2 dimensions. So light's doing exactly the same thing as gravity's doing in reverse. So you can just think of it as photons and being suntanned. And I could argue that all that's going to matter, right, if you're figuring out how much you're sitting here on the Earth, and let's just say there was a constant source of light. Let's just make it that way. And it's not coming from one place. It's not coming from the sun anymore. Let's just say the light came from all directions. Then you could understand that all the directions that can hit you, there are photons that are going to hit you in this direction. And the simple argument is might as well get right to it, is that the Earth is blocking, it's disrupting. It's like an opacancy, okay, and it's not allowing quite the same number to come this way. So for every photon coming from the universe, all right, from these directions that you can see uninterrupted versus these directions that are going to have to go through the Earth. And that's the differential. That's the differential you're sitting in right now, is that there's force, little bits of force, raining down on you like rain, okay, just like rain. And there's less rain that's able to get through the Earth. It has to go through the Earth, and it's being degraded in that process. Now, the simple truth is the Earth is molten in the center, which might give you some indication of where the energy that doesn't get here actually is. And where it actually is here in the center of the Earth, in this little hot spot. This is where the energy that should be here is. But anyway, so once you just accept that there's this plane, okay, that you're standing on, this plane here, and I could tilt that a little better probably, but anyway, and so as you rise up, you could understand that the higher I go, the more of this red stuff turns to blue stuff, right? So the higher I go, the more this blue is able to get to me because it doesn't go through the Earth anymore, right? So there's more angles, okay? My plane rises, there's more angles that it's equal, blue against blue, not blue against the weaker red in this case. And that's the inverse square law in another way of describing it. So the further away you go, the more this blocking feature, this degrading feature, isn't hitting you anymore, that cone. So as you're rising, you can understand that the cone here is on the flat surface, but as you rise, it gets more like this and more like this, and eventually there's just this straight line between you and another object. And so that's how tiny the actual force is that's actually straight down. It's not the straight down force. Okay, you're standing on the Earth and you think there's a straight down force pushing you down. Well, it's not a straight down force. Anything that hits you, any rock, okay, if it was a rock and we were hitting you with rocks, okay, and I hit you with a rock that has a 30-degree angle, that rock is still going to push you down. So anything that has any component in the downward direction is going to count as a hit down. Now, it won't be as much as a hit down, but it's still going to count as a hit down. So every time, while you're sitting here on Earth, you're not getting hit by gravity just down. You're getting hit at all angles in the downward direction. And you're getting hit less from all angles that have a component in the upward direction because the Earth is blocking you. Now, the truth is the Earth is round. Okay, so as soon as you rise a little bit, you start letting the real force get to you in the up direction, the undiluted force, and less of the blocked force is getting to you. And so that's why you, as you go higher, the force differential, the differential is highest here on the surface, and the difference, you get more and more blue the higher you go, and the less and less red gets to you. I guess I suppose I could have drawn this line as a red line, just to indicate that's all that's left of the gravity once you get further and further away. All that's going to be left is the ones that are going in a straight line. The little bits, the little rocks that are on a straight line heading right for you. And the same is true for light. The further away you get, only the photons that go in very straight lines from the source to you can possibly hit you anymore. Ones going at any angle can't hit you anymore. You become angularly tiny, and tinier and tinier, so you become very, very small, and only a tiny percentage of the photons can get to you. So this answers lots of questions about, you could argue about, well, how does gravity know that this, I could shape something differently, right? If gravity was just a downward force, you could argue that something this shape, okay, would behave different than something this shape. But the trick is, because the force is coming from all directions, that you can't fool it with shape, because this shape's going to get more of these, right? It gets less of these straight down ones, but it gets more of these sideways ones, a lot more. And obviously, in this case, it gets a lot less of the sideways hits and a lot more of the straight down hits. So the rain's coming at you from all directions is really kind of, It's not important to the end product, because the end product is just motion down. But there's a difference between me hitting two cue balls at angles, and hitting one, like say if I hit a ball with two balls and I hit this third ball. There is a difference between me hitting with one ball this way and me hitting it with two balls this way. I get the same end result, this goes this way, but it's being caused, okay, by a different, the truth is it's a different cause. So the real cause of gravity isn't straight down rain. The real cause of gravity is being hit by pressure from all directions, a light in the universe. The universe is lit up with what you could call gravity, and everything is just being pushed together. So things move towards each other because there's pressure in the universe, and there's less pressure between them, and they move towards each other. And that's the truth of it. And yes, that creates a little bit of problem with the notion of drag and different things, but all those things can be understood once you understand that electrons and protons don't. They actually do or experience drag. That's why they don't fly. I can't shoot a beam of electrons from the space station to the moon. It doesn't work. They won't go there. They won't get there because they are dragged to a halt. But if I take a helium nucleus, I can accomplish the task. So if I shoot matter to the moon, I can do that. But I can't shoot the elemental bits to the moon. They won't travel through the empty space. They won't make it. Their energy will be taken from them by the empty space. So there are ways to understand that drag is a real thing, but there is a way to overcome it, and that's called, a deuteron, but I won't get into all that. But so this is the important part. It's just to understand it's a push force, all right? And there's a reason the inverse square law isn't any more complicated than the inverse square law that the sun is doing every day. All right, every day the sun shoots a bunch of rays of light, and the fact is the further away you are, the less of those rays are going to hit you, because they're going to be spreading in 2 dimensions, and that's why there's an R squared rule. All right, so that's the quick of it. So the reason why things fall at the same speed is because each atom is doing this. Each atom is in a universe that's hitting it from all directions. Each electron and proton, and that's all they know. And all they know is how much stuff with a component from the bottom, the Earth, and how much is hitting them from the top. And the stuff from the top there's more of it than there is stuff coming from the bottom because the Earth has absorbed some of the energy coming from the bottom. It's that simple. So they all fall at the same rate. And all you're really doing is counting how many of them there are in an object, and it means nothing because they're all just individuals. It's just like you saying if I had a group of 10 people and they just were falling at the same time, I should think that the group of 10 people should fall faster than the group of 5 people. I put 5 people over here and I'm going to drop them. I'm going to drop 10 people over here. You wouldn't think these 10 are going to drop any faster because they're all individual people. They're going to all obey the same rules of acceleration and the gravity. So the fact that this one says it's more massive doesn't mean anything, except there's more people in this group. But it's the people that are falling. It's the electrons and protons that are falling, and they have a standard mass, and they move at exactly the same speed as each other, no matter how big a group they're in. So no matter whether it's part of a brontosaurus or whether it's part of a microbe, it doesn't matter. It's falling at the same rate. That electron will fall at the same rate, because as much as it's part of something, it's really just an individual. And it's the individuals that are getting pushed by the gravity, the individual pieces of matter. All right, that might be enough of a start, and then we'll re-say some of it, because he's going to say some more crap that's going to provoke a counter-argument that, no, it doesn't work that way. All right, I probably should have put in here the simple rules of how this energy from gravity is collected. So if you can accept that it's little bits of little tiny particles of gravity all moving the speed of light, and if I put them at a frequency going in a direction, they end up being light and other things. But no, let's just say these are the ones that aren't at a frequency. They're just reigning in the universe. The full universe is full of little bits of stuff flying the speed of light. Just like your cell phone and all this other stuff, they're just little bits of something moving the speed of light in all directions with clear direction. And so what are the banging in rules? So if I'm sitting here and I get hit by one, okay, and it's going, and I'm already going in that direction, or I'm stationary, all right, it's just going to basically stick to me. The little bit will stick to me, and it'll share its velocity with me. So let's say I weigh artificially 10 times what it does. Then you could understand that I'm going to get 1/10. This electron will get 1/10, okay, of the velocity that this has, and it now will be an object going through space that's a little heavier than it was. It has one mass plus 1/10. All right, and if another one hits and it sticks, and another one sticks, and another one sticks, and another one sticks, you can understand it starts going half the speed of light, because enough stuff has stuck to it. And the simple rule is, if something comes from the opposite direction, if something hits from the opposite direction, it will be just a standard kinetic elastic circumstance. This will come in from this direction, this one's already going in this direction, and what will happen is this one will reflect and this one will reflect. They reflect in a straight line, but I'm just making it clear that that's all you get. You just lose one of these that you've collected, so your speed goes down 1 unit of velocity, and this one goes back the way it came, and that's what happens. So you can't collect anything in both directions. You can only collect in one direction at a time, and so basically it's just add and subtract. How many things hit you from this direction versus how many things from this direction. If you have more stuff has hit you from one side than the other side, then that's the direction you're going to go moving in. And so those are the simple mechanical rules. So it's like you're collecting rain in a bucket. So you could just think of gravity. Your mass just tells you how big is the bucket, how many little bits am I actually going to move. All right, and you're just going to catch the force. So if you have more pieces of matter and you give them all velocity, the velocity of all those pieces of matter will add up. Okay, and so even though you have, the 10 people in one bucket over here, you could argue, and the 5 over here, you can simply understand this is going to hit the ground harder because there's more people here to push into the ground, more people to smash the ground. All right, going the same speed. So this will be twice the impact that this will be if it's twice the velocity. If you drop this from 4 times the height, obviously. But it's that simple. So when the bucket rubs against something, let's just say you rub against this bucket so it can't free fall. It's something less than free fall. Well, that's taking water out of the bucket. When the bucket hits the ground, all the water leaves the bucket. So the force can only stay in as long as there's no counter force to make it all reflect away. But the force is this stuff you collected. You collect force. Things that move have little bits of energy stuck to them, and those little bits are basically just transferred. You can give them to something else, and you can take them from something else. But the simple rule is just kinetic. It either sticks to you, the force, or it causes a reflection where both elements of force are lost. It's either a pure reflection or it sticks entirely. That said, now we can go back to the video. Sorry I'm playing it fast. It's just for, expedience, and it just makes the whole process a little bit better, I think, for absorbing. It's not saying anything terribly complicated here, so I will paraphrase what is said.
Around to the end of this lesson, you will understand about all that we know about why this actually happens. And it is still one of the most interesting, not totally well understood ideas in all of physics, but we can certainly get to the meat of the matter and talk about it.
So again, he's not going to get to the meat of the matter, because the meat of the matter is that this is about single elements of mass, and it's not about objects. It's about the elemental universe, what the smallest universe, what the only universe is doing. There's only one universe. It's the little tiny one with the electrons and protons, and everything else is just emergent mush. Everything else is following the rules, and the rules exist for the electrons and protons. The rules don't exist for bigger objects. Cactuses and lizards and whatever, birds and butterflies, all that stuff, okay, isn't the real thing okay, making that stuff happen. The real thing is the electrons and protons did it first.
Before we get to that, we want to talk about gravitational acceleration. So gravitational acceleration. Now, in the last few lessons, we've been talking about things accelerating, and that was always on the x-axis here, in one direction. Now, when we talk about things moving in the up and down direction on Earth here, we call it the y direction. And because we're dealing in the y direction, the acceleration that you feel in the up and down direction is the acceleration due to the gravitational force of attraction between the Earth and all the bodies that.
So it's not attraction; it's frankly just a push. Okay, so there's no pulling involved, and it's just a simple mechanism. You're getting pushed more from the universe, the undiluted universe, than you are getting pushed from the opaque Earth.
Surround the Earth, okay? So what we say, then, is that the gravitational acceleration g is equal to the value of 9.8 meters per second squared. It's really
So this is where they go wrong, all right? That's not what Newton said. It's not what even Galileo or Descartes were so close to figuring out. It's simply 9.8. No, I should erase. All right, if I didn't say so earlier, let's understand this guy worked for NASA. Okay, this is a true NASA scientist, and it's very disappointing, that they can't get this. They can't be honest, or they can't describe the reality in more honest terms. It's 9.8 as a number, all right, and the meters basically means it's times 1 meter. Okay, that's how you get the meters. It's 9.8 meters, okay, basically because it's 9.8 is your number times 1 meter. And the seconds, okay, is just 1 second down here. It's per 1 second. It's a ratio. It's a ratio of 9.8 for every 1 second. And that's exactly how it works. Exactly. I mean, if you drop something from 4 times the height, it's twice the time. So what does that mean? Well, yeah, it means you get 9.8 up here when you drop the first 4.9 meters. And then in this whole giant hunk here, you're only going to get 1 more unit of time and only 1 more unit of 9.8. And that's why you land with 19.6 of velocity. It's because you only got 2 units and 2 units of time. 1 unit of time, 9.8. 2 units of time, this number has to be 19.6. A half second of time would be 4.9. You can't keep this number and change this number. So it's 9.8 per meters per second, and that's all it is. It is not seconds squared. The acceleration is 9.8 meters, okay, per 1 second. There is no seconds squared. There is no seconds involved. There's just 1 second involved. It's in 1 second units. That's how you acquire the 9.8 change. All that's changing is your velocity. Your velocity starts in the first second, you gain that much of it, and in the next 1 whole second, all you're going to gain is that much. That's all that's going to change in your velocity. Now the distance you'll travel will be twice that distance because you're going 9.8 here. This 9.8 means you're traveling 9.8 when this is all free. You didn't have to do any work for these 2 units of distance because you already acquired that velocity. Your change was 9.8. That change means you're going 9.8. It means you traveled this distance without having any extra force added. And now you're going to add 1 more unit of 4.9 distance and 9.8 in extra velocity when you finally hit this surface. It's only 2 units of 9.8. It's just wrong. It's not Newton's. It's not how Newton formalized it. It's not how Newton described it. Newton would never have said per second per second. And he certainly wouldn't write per second a second squared. Saying something can happen for multiple seconds is not saying square the seconds. The two things don't equal each other. A square on a number, okay, is not saying, yes, you have 5 times 3 seconds, or you have 1 times 7 seconds, or some other. It's 2 different numbers. You can't say second squared because one of those seconds that you're squaring is a different number than the first one. The first one's a 1. I mean, 1 squared is harmless, but that's not what they convert this into. They use this mathematical trick to convert it into saying this little squared here gives them an excuse to say we're going to square an actual number. It's not harmless. It's not 1 squared anymore. It's not 1 second squared anymore. When they move it around in a formula, the 1 is lost, and the only thing that exists is the s. Yeah.
9.81 with a bunch of decimals after it. But this is a good approximation to solve pretty much all physics problems. 9.8 meters per second squared.
So it isn't squared. It's only 9.8 meters per single second. So 1 second, I go 9.8. 2 seconds, I go 19.6. 3 seconds, I go 39 point whatever. 4 seconds, it's just adding 9.8 per second per single extra second.
So what this unit means is 9.8 and meters per second squared. Don't forget what it means. It means meters per second in the top per second. That's meters per second.
So that's what it doesn't mean. So obviously anybody can look at that and say, well, that doesn't what it means. It means there's seconds times 3 multiplied. You can't be dividing seconds into seconds and say that's second squared. That makes absolutely 0 sense. Usually when I divide something into something, I make it go away. So yeah, that's a fraud. So this is where they do their fake cross multiply and say, well, let's put a 1 over s here and turn it into a fraction. Okay. And now they can inverse them and go second squared. But it's not honest. It's just a mathematical gimmick.
Second squared. So this is how much your velocity increases every second. So if I drop something, after the first second, it is going from rest. Now at the first second, it's traveling at 9.8 meters per second.
Right. So in 1 second, all it got was 9.8. It didn't get anything squared. It just got 9.8, period. End. No squared functions anywhere.
But after the next second, it picks up an extra 9.8 meters per second.
Yes, only 1 extra 9.8. So all it got was 2 9.8s. It didn't get 4 9.8s. It didn't get some squared function of 9.8. It just merely got 2 units of force, period. And that's all that's shown. 2 units at 4 times the distance is just 2 units of time. It's only 2 units of velocity, and you've only increased your weight by 2. So all those 2's they ignore. The NASA scientist says, I don't know what a 2 is or whatever, and they pay attention to this distance crap, which doesn't mean anything because most of your distance will be accrued velocity. It won't be a change in your velocity. That's the part that your velocity is doing as a constant force. The 9.8 is still in there and pushing. This 9.8 will still be in there and pushing. Every 9.8 you get just keeps pushing and pushing and pushing. The velocity is unending. It's enduring. You're not getting a new one each time to keep pushing it. I mean, it's just wrong.
Second velocity. After the next second, it picks up another one and another one. So every second, it's picking up 9.8 meters per second. That's why it's called 9.8 meters per second, which is 9.
Yeah, right. But it's not. That's not what it's called by reasonable people. That's what it's called by people who are just playing a game. You don't go 60 miles per hour per hour. Nobody says it. It's not what you say because it's not what you do. It's not the truth. Okay, we already know that it could take 10 hours or it could take 7 hours or it could take 6 hours. I could be going 60 miles for all kinds of different amount of time. Why would I square the miles per hour? That wouldn't make any sense. So if I said 60 miles per hour, then every time I put like 4 hours in there, I end up with 16 hours. I didn't drive for 16 hours. It's not a squared function, but they need the squared function to justify their kinetic energy nonsense.
0.8 meters per second squared. All right, now, in all of our equations of motion, these are, remember, our equations.
So all these equations can be changed and modified by merely understanding that every time they square the time, they're really just saying that the real truth is, the real physical fact is there's a clear relationship between the distance that quadratically increases. So the distance goes, Galileo, 500 years ago, figured that out. The distance is quadratic. The distance keeps growing. So your total distance, if you take the square root of your total distance, it will tell you how many seconds you were in the gravity. So that's how simple it is. It's 1, 3, 5, 7 is the extra amount of velocity you got for free, so to speak. The stuff that you're getting for free. right? The second, how much free energy did you really get? You know, right, that's probably the wrong way to say it. So never mind that last couple of sentences. But the relationship is every time he says t squared, he could put square root of the distance. And well, t squared is the distance. Let's understand. So the t squared is just another way of saying the distance, okay, total distance. And so you could say it just the opposite way if you needed it. But that's all it's really doing. Every time the time is squared, it's just basically saying the total distance, because that's what it'll equal. The time squared will be the total distance. So you could just put distance in here instead of a t squared, and distance in here instead of t squared. And it'll work exactly the same because the distance is the time squared.
Equations of motion.
More importantly, the time is the square root of the total distance. That's the actual thing that's growing quadratically, is the distance. The time isn't changing. The time isn't growing quadratically. The distance is, the total distance.
Use these to solve problems in a minute, but in our equations of motion, we have the acceleration a. So what we're going to actually do is we're going to use the exact same equations of motion, but we're going to say that the acceleration a is equal to negative g, which is negative 9.8 meters per second squared. Now you might say, why?
So this is where they play a game like we need positive and negative numbers as if they're going to be any real positive and negative functions here. There's only a positive function, frankly. If you're going up against gravity, you're going to watch your acceleration decline, okay, and your velocity decline. And if you're falling with the force is adding. So it's either subtracting or adding to your velocity, but you're not going to be doing both. You're either doing one experiment, you're either falling in gravity or you're pushing up against gravity. You can't do both at the same time.
Why is he putting a negative sign in here? Well, it's because when we are dealing in the horizontal direction, we have the positive x direction and the negative x direction. And when we're dealing in the vertical direction, what we do is we say that we have a plus y direction up here.
I mean, why would somebody bother explaining these arbitrary assignments of plus and minus? I mean, again, it's who's the video for?
In a negative y direction down here. So here's the 0 point, which could be any reference point you want, but it could be the ground, for instance. And then going up, we call it positive y. Going down, we call it negative y. But since gravity always acts
well, obviously the ground wouldn't be a negative, but whatever.
Downward, we call the letter g being equal to 9.8 meters per second squared. The acceleration, when we put the correct sign on it, we say it's negative 9.8 meters per second squared because the acceleration of gravity acts down towards the ground. So when we solve
towards the center of the Earth. So again, you're not going negative really until you get to the other side of the center of the Earth, but whatever.
All of the problems involving motion due to gravity, then since we choose the up direction to be positive y, the acceleration is always acting opposite to the up direction, so it's negative g, or negative 9.8 meters per second squared. So what we're going to do in a minute to solve these problems is we're going to transform these equations very, very simply into equations we can use in the up and down direction. We call this free fall acceleration problems. But before we get to that, I want to tackle one of the most interesting things in all of physics, and that is, let's go back to the idea that if we stand here and if you drop a bowling ball, which is very heavy, and a paperclip or a pencil, then actually they will hit the ground at the same time. In fact, if you take a car, a vehicle, a dump truck, a gigantic wrecking ball, anything, and you suspend it in the air, it's very massive, very heavy.
Right, and if you just think of it being made out of individual units that are quanta, so if you think of it in a quantum mechanical kind of way, and that the individual units are basically the thing that's going to be affected by the force, and they can't be affected differently, that each electron is going to absorb the force exactly the same as every other one. Again, you could just think of it as made out of ducks, and each duck is an independent duck. So in the wrecking ball you have 500 ducks, and the other thing you have one duck, but there's no reason to think the 500 ducks can move faster. They can't. They can only move as fast as ducks are moved by gravity.
Heavy. And you also grab a pencil, and if you could ignore air resistance and you let them drop at the same time, the very heavy object accelerates down and hits the ground at exactly the same time as the lighter object. If you ever see that not happening on Earth, it's only because the air is in the way. You take the air out of the equation, as on the moon, they always hit the ground at the same time, no matter what the difference in the mass is between the objects. Now you might say, how is that possible? People have been pondering this for years, thousands of years, right? Because...
So again, they did ponder it, they did have answers to it. So again, Descartes had his answers, Galileo had his answer, Newton has his answers. They're probably not perfect answers either, but they all did start to get to this idea of the essence of something is made of pieces, that we're made of parts. And they certainly, I think Galileo and Descartes certainly had a whiff of the fact that the complex organism is made out of little bits that are moving, and those little bits, in the case of inelastic collisions, for example, will take the momentum and move in lots of other directions. They won't, you can put something in left and you can put something in right, and it goes into something and it ends up moving in all kinds of directions. And so it lost its direction, but it's still energy all moving in lines, but they're not moving in the same direction. So they're not going to be as obvious because the energy has moved little pieces, lots of different directions.
It seems like a heavier object should hit the ground first. Why? Because we know that heavy objects are pulled towards the ground more.
So there's no pulling, it's a push universe. So again, a NASA engineer who hasn't, see, you have to think about stuff and you're just saying, well, yeah, okay, you didn't think about it very hard. That really, where's this idea of pull come in? It can only come in on the most tiniest universe. We all know that big things don't pull on anything. They don't have arms and they reach out and pull, whatever that would mean. And every time you pull, you're really pushing on the back of something. I mean, they know this. When you pull on a rope, you're really pushing on the fibers of the rope. The rope doesn't feel any pull. It feels you pushing on the rope. So, shouldn't really be a subject, frankly, which all should agree, like we agree on the metric system or something, that frankly every real event of a transfer of motion is a push transfer. Motion is transferred through pushing, not pulling.
So if they're pulled to the ground more, they should accelerate more and they should hit the ground more at a sooner or a smaller amount of time. So why is it when we do this experiment, and I encourage you to do it, go grab a marker, go grab a penny or something small and drop them, and you'll see that they always hit the ground at the same time. Why is it? We know the more massive object is attracted more and has a higher force of gravity.
So again, it has a higher force of gravity. It doesn't have any such thing, okay? It just doesn't. It doesn't have a higher force of gravity. It has more individual bits, and basically it's just more bullets. And you're saying if I put more bullets in my gun and I shoot my gun and all the bits are going 10 miles an hour, well, yeah, if I get hit by one bit, that's not so big. But I get hit by 1,000,000 bits going 10 miles an hour, well, that's a lot. You're just getting hit by more bits of matter. That's the only difference. But they're all going the same speed. But getting hit by more matters.
So why doesn't it just accelerate more and hit the ground at the same time? Well, in order to do that, we need to talk a little bit about some things we haven't discussed in physics yet. So I'm going to get a little bit ahead of where we are. We're going to talk about gravitational force.
I don't know where we are. Where are we? The fourth grade? I mean, I don't know. Where are you?
And we're going to talk about one of Newton's laws of motion.
I mean, there's no way you jump to these equations in the fourth grade. So, I don't know where he's going here.
We haven't really had those lessons yet, but I don't want to wait because it really is one of the most interesting things in all of physics, and I just can't teach this lesson on gravitational acceleration without sharing with you one of the most amazing things you could ever learn.
So he keeps saying this, right? So I played the whole video. I was going to just cut it, get to the parts where he says something directly, but you can see he just keeps emphasizing and emphasizing and emphasizing, and it really isn't that significant an idea once you recognize that it's the electrons and protons that are actually being affected by the gravity. That really doesn't have anything to do with us. Okay, we're not being moved by the gravity. The little bits that make you up are being moved by the gravity. And the little bits are individual little bits, and they're individually being pushed. And as individuals, they're all the same size, and they're all the same thing, and so they all have to move the same way.
Why is it that two different objects of two different masses hit the ground at the same time? So we're going to get a little ahead of ourselves, but then we will catch up, and we will hit gravity and some other topics a little more thoroughly later on. So the first thing we need to understand in order to understand this is we have the force of gravity. Right?
So the force of gravity is the absence of gravity. So it's the absence of force coming up. That's all it is. So the Earth is producing less heat, you could argue, than the universe is. The universe is pushing with a certain amount of heat, and the Earth, for whatever reason, just has a little bit less coming out of it. Now, I'd say the obvious reason is because the Earth is made out of matter and the matter is being moved, and the movement is absorption of the energy, as pointed out. So the energy is moving in lots of other directions except going straight line. It goes in as a straight line and it starts moving all over the place inside the Earth, and that's the problem. So it doesn't get to the surface when it should, and that's why you end up in a differential.
So the force of gravity is a famous equation. Here's what it is. the force of gravity, you call it F sub g if you want, right? You have a little object here. It's got some mass. There's some earth down here. Let's call this earth, right? And there is some force acting on.
So this was, I think, a mistake of Newton, was to combine the two forces, because they're individual forces. This has its own gravitational field it's creating. Every mass is going to absorb energy and create a differential. So everything that has any mass to it, any electrons or protons, it gets moved. In moving, it's absorbing energy from the outside field. So whenever there's a piece of mass, you could say it's really cold or it's really hot. I guess the better argument is it's hot. It's absorbed heat from the universe. And it's taken it out of the active universe, however you want to describe it. And so there's a differential, and that's the gravity well. So everything has its own well, and I don't see much point in combining this well with this well. They probably should be kept separate. The Earth has a gravitational field creating 9.8 meters per second. This little piece of crud doesn't have much to do with that. Doesn't have anything to do with that, frankly.
On this mass, because the Earth has some mass, big M. I'm going to call it big M, and we're going to call it big M with a little e on the bottom, because this is the Earth mass, gigantic thing, right? And then we have a smaller mass, which is you or me or anything else, and it's sitting up there and has a mass little m. Okay. Now we know from experience that there is a force acting on this thing. We're going to call it F sub g because it's a force of gravity. If the thing is over here or over here,
that's the force being caused by the Earth. So the Earth is absorbing energy, creating a differential. That's this force. Okay, it's just the differential being created by the Earth. Now, obviously, this thing's creating a differential, but there's no way the matter on the Earth could give a care because this is so much smaller. It can't radiate enough photons to matter, so to speak. It's, I don't know how to even make a comparison between the Earth and something standing on it besides making a comparison between a man standing next to the sun and pretending he's significant in terms of how much light he's producing. It would be ridiculous.
Over here, the force of gravity always acts toward the center of the planet. So the people on the other side of the planet are pulled kind of up to their local ground, and everybody...
Yeah, not pulled. So again, this keeps using these trigger words. There's no pulling in the universe. It's not a scientific concept. In my opinion, physics should be way past this by now. This should have been figured out a long time ago. Pull isn't a reasonable idea. It's just not. It has to always be considered the absence of a push. There's a pull because there's a missing counterforce. It's the missing force that creates the idea of a pull, but that's all there ever is an imbalance. And the imbalance is always because something else got pushed more, not because something got pulled more. Alright, continuing.
Being attracted toward the center with F sub g, the force of gravity. And we already know that the more massive you are, the more force of gravity you feel. A car has...
No, the more you'll collect. Period. And what you feel, again, it's talking about what we feel. We don't, what do we know? Right? I mean, our mass isn't what makes us feel gravity. So, that just doesn't make any sense at all. So, I think we all feel the same gravity. No matter how much you weigh, you feel the same gravity. Obviously, your fat arm is going to weigh more. You can figure that out. So, I don't know. It's just wrong to interject with words like feel your gravity.
There's more force of gravity than this marker, for instance. So, this force of gravity.
You're carrying more mass. It's just a fact. You carry more stuff. Carrying stuff is heavy. Yes, that's the name of the game. You got more stuff to drag along. So if you want to drag it somewhere or move it somewhere, you have to move more stuff. That means you have to hit it with more force. So you have to create more force to make it move. Something big with lots of little bits in it, okay, is just the difference between 1 bullet and 10 bullets. It's just how many pieces of matter do you have, and you're just saying they're going to move at the same speed and hit the ground. Well, yeah, where there's more bits of matter hitting the ground, there's going to be more dents in the ground. No big surprise.
Is called F sub g, and it's a famous equation, right? And here's what it is. It's the gravitational constant of the universe, g. We can look up that number later on.
It's a little funny that he has notes. Because this one should be so fixed in his head that he shouldn't have to look at a note for that one.
And then it's multiplied by little m, and then multiplied by big M, and then divided by r squared. So, it's an equation, but as equations go, it's not that.
Right, and so the r squared part isn't just Newton's. A few people were already speculating about that one before Newton came along. because they were thinking about it as rays and vectors of gravity and blah 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 blah. But yes, it's as simple as this right here. This hand is 4 times smaller than this hand at half the distance, right? This hand at half the distance from the camera is 4 times bigger than this hand, only twice that distance. So twice the distance, 4 times smaller. Because the same thing, the camera's doing the same thing to the photons that the sun does, that it all does. The cone that you can see, the part of my hand that is your total field of view, is getting smaller and smaller. A smaller and smaller number of photons are hitting it at the inverse square law. So you can think of it how light comes off a light bulb. You can think about how objects become bigger and smaller with distance when they don't really become smaller, right? You know this isn't really a smaller hand. All right. But that's the inverse square law. And gravity's doing the same exact thing, making it pretty easy to recognize this isn't about some kind of bent space. This is about a force, like a photon, that's spreading with distance, that's weakening with distance.
Complicated. Basically, you have a constant of the universe called G. This is the gravitational constant that governs everything. We can look the number up in a book, but honestly, the number doesn't matter. It's a constant we can look up.
It's an important concept because that's the thing that regularizes it, makes it so you can compare anything and just compare it based on this r squared. So it just gives you the capacity to recognize that there's a certain factor of distance and there'll be a number. And that's how they derive the 9.8, is because the 9.8 is a derivative, okay, of the r and the g.
Big M, little m, divided by r squared. So you can see right away that if you make the mass of yourself bigger, then force of gravity gets bigger. If you make the mass of the Earth bigger, that's going to be the mass of the Earth right here, then the force of gravity gets bigger. If you change the constant of the universe and make it bigger, then the force of gravity gets bigger, but that constant doesn't change as far as we know.
Right. Well, at least it says as far as we know. I'd say it probably changes over time because galaxies get tighter and bigger. As galaxies shrink and grow, the amount of energy free versus energy trapped connected to an electron or proton, those numbers change. So as more and more energy gets stuck to matter, then there's less energy in the universe. You could understand there's less free energy. And as more and more of that force is released from matter, that is, matter moves slower and slower, then there's more force, which means more pressure.
Now, what if the distance between the object, because this is the distance, r, between the center, I've drawn it to the surface, but really it's to the center of the Earth here. So I guess I could clarify that and say this r is to the center of mass of the Earth there.
It's always relative, so it really doesn't matter. All you're usually making is relative comparison. So for relative comparison, it doesn't matter where you take the r from, as long as it's proportional. So you can forget about the center of the Earth if you weren't doing this G equation. Sorry, the G equation requires you to use the center of the Earth.
Increase, make the distance bigger between the two objects, then this number gets bigger and the force of gravity goes down. And that makes sense because if I pull something far away from the Earth, we expect there to be less gravity. And that's what happens. If we go thousands of kilometers away, the force of gravity is smaller because the
Wouldn't it be smarter just to say it gets smaller because it's diluting, it's spreading, it's getting thinner and thinner? It's the area of the square that the photons are hitting, or the energy is hitting, the square is getting bigger and bigger and bigger with distance. And the amount of stuff I'm throwing at it is the same. So it's like a paint sprayer. Right? Another good example. The further away I am from the paint sprayer, the less of the paint that gets on that surface. Because the paint is doing this cone thing, and I'm only a smaller and smaller part of the cone.
distance is bigger, and so we divide by a big number, we get a small gravity. If we get close to the surface and make this a very small number, then this number gets bigger. So this is the force of gravity, right? Now the next thing we need to know...
So it's really not the force of gravity, because he's using both objects' gravity as part of so he's combining both of their gravities. So it's really not a clear description of the function of gravity being created by an object of a collection of electrons and protons. Each collection creates its own gravitational field.
It's something called Newton's law. One of Newton's law of motion. We're going to talk about this a lot more later, right? What we have...
So this will be the big lie, because they can't describe these accurately to save their butts.
with Newton's law is a famous equation called F is equal to ma.
All right, so it's not Newton's equation. That's not what Newton said. And to be clear, when they pervert this F equals ma crap into creating a square to create 1/2 mv squared, Newton directly opposed it. So Newton directly stated clearly, twice the force, twice the velocity. 3 times the force, 3 times the velocity. 4 times the force, 4 times the velocity. Newton did not agree with this formulation. This is not Newton's law. This is not Newton's math. This is not Newton's science. This is not Newton's physics. It's not Newton's understanding. It's just a lie. Einstein wouldn't agree when people say there's Einstein rings. We've seen them. Einstein would object and say, don't call it after me because my science can't do that.
Since the force acting on an object is equal to the mass of the object, notice it's little m, same little m as over here, times its acceleration. This is, there's a joke that says that if you know F equals ma, the Newton's law of motion.
Right, so it's not Newton's law of motion, it's not Newton's formulation, it's not Newton's physics, it's not what Newton agreed with. And so they're saying, yes, if you know this fake thing that isn't Newton's science, that somehow you know everything. No, you know everything if you know F equals change in your momentum. That's what Newton overtly stated. You want to know the force, you look for the change in your momentum. You want to change something's momentum, you just add the same amount of force as the momentum you want to exchange. He said it's clearly proportional. Force is clearly proportional to momentum. Perfectly exchangeable. You just add a force if you want to increase the momentum.
Then you can solve almost any physics problem, because most physics problems, a lot of them, boil down to just knowing how to use that equation properly. And we're going to use that.
So they're not going to use it properly. It's not right. It's not fair to Newton. It's just bad science. It's bad. It's rude. Okay. It's bad human behavior. It's not good logic. It's not good reasoning. It's not good science. It's not good figuring. It's not good detective work. It's not responsible in any way to sit there and cheat the facts that grotesquely. Those aren't facts.
Equation a lot coming up. But what I want you to know and pick up from this equation is this is kind of like the law of inertia. You know, you already know that if you were to get...
There's no such thing as inertia. Inertia is just another word for mass. Mass doesn't resist being moved. It just requires you to give it the movement. Saying something doesn't want to be pushed doesn't make much sense. I mean, saying, well, you're not moving. What, don't you want to be pushed? No, it's saying push me and I'll move. But you have to push me. If you're not going to push me, I'm not going to move. Yeah, you want to change my velocity? Well, you have to apply a force. I'm not going to change it for no reason. So apply a reason and I'll be obedient. There's no resistance to change. You just have to make the change. If you're not going to make a change, then nothing's going to change. But to say there's a resistance? No, you have to give something. If you want the homeless guy to have $10, you have to pull the $10 out of what you have and give it to him. And now you're going to be poorer. It's just a fact. There's no other way to do it.
Go into deep space and you push on something, like a spacecraft or a basketball, then it should start moving, right? So this equation tells me...
It will start moving, and it won't say, no, I don't want to move. It won't do any of that crap. Now, if the object is so massive and what you're giving it is a little tiny... it's not going to go anywhere. It's going to say, forget it, I'm not going anywhere. You didn't give me nearly enough energy to move all of my atoms. All my atoms have to move or I don't go anywhere. So you can vibrate me if you want. You can ping on me and I'll go ping and I'll vibrate, but I'm not going to go anywhere.
Push on something, that's what a force is. The acceleration that happens is related by this equation. If I know the mass of the object and I push on the object, then I can calculate the acceleration that the object will have.
So, and again, but you'll be calculating a wrong squared number because it's not something squared. There's just a unit of change. The unit of change is in the exact same substance that the velocity is made out of. All you can do is add more pieces of velocity, or you could subtract pieces of velocity. But that's all an acceleration is either a subtraction of a velocity or the addition of a velocity. It is not a squared function.
Because it's going to start to move. Now you know from just dealing with things on the ground, if I go behind a giant semi-truck, which has a lot of mass, and I push on it, it's very hard to move. But if I go up to a tennis ball with a low mass, it's very...
Right, but it's going to move. I mean, it's just like saying in space, it's going to be a lot easier to move because then you don't have static friction. So static friction is a little bit, it's a complication. But that just has to do with the fact that things sink into the ground and you have to push them out of their hole. But, freely speaking, the amount of force you'll be applying per unit of mass will still be the same. You have no expectation the truck is going to move just as fast as you pushing 2 people. Yes, pushing 4 people means you have to give 4 people $10. If you push 2 people, you only have to give 2 people $10. So obviously if you push 4 people and you only have $20, well, then you have to give them $5 bills. And if there's 8 people, well, then you have to give them $2 bills. You know, you have to cut the amount of what you're going to give them into little tinier and tinier pieces. The more mass they have, the more hands that need $1. Yeah, you have to break the money into pennies. Big objects, you can only give it. You'll spend $20, but you'll only give away pennies to each individual.
Easy to move. That's what we call inertia. It has nothing to do with gravity.
So again, it has nothing to do with reality. There's no such thing. It's just mass. And mass doesn't resist movement. It just demands that you give it movement. It will not have movement unless you give it movement. You have to give it energy for it to have energy. You have to give it momentum for it to have momentum.
Into deep space with a semi-truck and try to push it. It's going to move, but it's going to be really hard to get moving. Even though...
And so again, it's not really hard to get moving. It's just going to move slower because there's more of them. You have to give them pennies. You can't give them dimes. You can't give them quarters. You can't give them dollar bills. You have to break it into small units of food, so to speak. And so, yes, you'll get less out of each person because you gave them less per person. You gave each electron less energy.
There's no gravity, okay? Tennis ball in space, very easy to move. It's because the mass is different. Somehow, the mass of an object resists motion, right?
So it doesn't. No, it's not right. It's not resisting motion. It's just the fact is that there's more motion has to be spread over more things. There's the same, you can't say it's the same amount of bread and butter, right? If I double the size of the bread that I have to put the butter on, well, obviously I can't expect the butter to be as thick. And it has to get thinner and thinner and thinner the more bread I create. The more bread I'm spreading the butter on, the thinner the butter is. I mean, this isn't even a little bit complicated.
When you have more mass in an object, it resists your push. It does start moving, but it takes, more effort to move.
If you apply 20 pounds of pressure, okay, for a certain amount of time, then you'll get exactly what you put in out, okay? So if it's a light object, it'll go 10 miles an hour. If it's a heavy object, it might go 1 mile an hour. Those are the simple rules. But you're moved the same amount of total mass is moving the same amount of total MV. You created the same momentum because the force is momentum. Maybe I should just end there, come back to this. Where are we at? An hour. Yeah, that's probably the right thing to do. So yeah, maybe I'll make a part 2 or 3. We'll see how it goes. I mean, once he gets into the math, there's probably no point because it's just all contrived crapomatics. That's it. It's designed and contrived to circularly justify itself, and you can see that in the work equation. Again, his physics, NASA physics says I'm holding a barbell that weighs 100 pounds, and I'm not doing any work. Or I take a barbell and I lift it really slowly. So it's taken 1 hour to lift it 1 foot. They say I only did a foot worth of work. And we know that's not true. We know that if I moved it at a certain speed, the ideal speed, I would lift it at a velocity. I would jerk it, And by lifting it at a quick enough velocity, I would substantially reduce how much work I have to do to lift it. That's why weightlifters jerk weights. It's because the whole idea is to give the weight as much velocity as possible initially so they don't have to do the work. They don't have to spend as much time fighting the gravity. The less time you push against the force, the less you're in the rain. The faster you move through the rain, the less rain that hits you. That's what a weightlifter's trying to accomplish. That's the real definition of work in the world. The real definition of work is force times time. It's how long you're applying a force or how long you're fighting a force. That decides how much work you do. Distance is a trivial consequence. It isn't the cause. All right, so I've given you the real truth, okay? Everything I said here was probably pretty close to something that won't that will be almost perfectly true. All right, I mean, I could have explained positive and negative charge and all that stuff, but these basic arguments are going to be turned out someday to be the real truth. And this bent space crap and this illusionary fake idea that gravity is not a force, it's not a real momentum exchanger, that it's not real momentum that's hitting us from the universe, it's not real pressure that's pushing the sun into a little ball, that's not real pressure, that's just some geodesic that did it, some bent spacey thing is pushing the sun into a round ball. No, it's a real force, it's real crap in the universe moving, and that real crap is moving the speed of light, and it is invisible to us. That's just a fact, okay? It's invisible, and beyond this, okay? I mean, this is sort of a giveaway, right? You can sort of see that it must be there because, well, look what it's doing. But that's the fact. That only moves because it's a differential in the energy above the object and below the object. And above and below in terms of all vectors of hitting. Okay. That is going to be the truth. I'm sorry. For the rest of humankind after, okay, the day when you finally grow some integrity and start speaking the truth. When you stop lying about what Newton said and you go back and you think about all of the ideas that were still in the realm of reasonable, okay, before you accepted Leibnizian's wrong statement. So again, Leibniz said it's the same force to lift 4 pounds 1 foot as it is to lift 1 pound 4 feet. It's not the truth. It's a false axiom. It's a false statement. That's what their physics admires and is built upon. And de Châtelet in the 1735 issues decide to tell us that I can measure energy by measuring how much a round thing dents clay, and that'll tell you the truth. And then they made arguments about, well, you could roll something on a surface and it rolls twice as far, 4 times as far when you give it just twice the velocity. Well, it rolls 4 times as far is because it's not as much friction when it's moving faster. A NASA scientist should be able to figure that part out. I think a NASA scientist knows that when you roll something, it goes half the speed after it traveled 3/4 of the distance. He's a NASA scientist. He probably knows that. So that's a really important truth. You talk about important truths. That's a gigantically important truth in telling you, oh yeah, this is all sort of bullshit. This is 9.8 right here. 4 times the distance, right? It's going half the speed and it only went 1/4 of the distance. At 1/4 of the distance, it's already going half the speed. It's a huge tell that this force isn't linear. No way. Oh, come on. I shouldn't. It's embarrassing for the human race that they're so dishonest and have so little integrity that they play this game that they've got the right answers when these answers are clearly not right. There's no pull. It's a push universe. It's clearly gravity's a force. It's not some fake, phony, bent thing, bent ether or whatever the hell they think it is, a bent something or other. That's their definition of the reality. It's a bent something or other. They damn well know if I sit there and pick up a heavy thing and I lift it really, really slowly, I'm going to do a lot more work than if I lift it quickly. They know that's the truth. But their formula says, who cares how long it took you to lift it? You did the same amount of work. No matter how quickly you lift it, it's the same work. It's not. It's garbage. It's junk as science. They ought to be ashamed of themselves. Maybe someday they will. We'll see how long it takes for the truth to get out. And the truth that's being suppressed by all these naysayers who can't produce a single piece of reasonable evidence to counter anything. They have never proven. This guy is going to tell me he believes it takes 9 times the fuel to go 3 times as fast, or 25 times the fuel to go 5 times as fast. He knows that's not true. Yet he's defending a physics that says so. I mean, really, it's disgusting that I have to make this argument and all this hostility when, I mean, come on. It's just clearly mistakes have been made. Just fess up and fix it. Damn it. All right, till the next time, such.